In the last chapter, we learned about data flow analyses with monotone frameworks. Our analysis mapped nodes in a CFG to elements of a lattice. To solve the constraints, we found a fixed point of our constraints. Finding a fixed point required a finite height lattice. If we didn't have a finite height lattice, our algorithm for finding fixed points wouldn't necessarily converge. In this chapter, we'll study a way to get around this limitation called widening. Let's start by studying a new analysis problem called interval analysis. In interval analysis, our goal is to determine a lower and upper bound for every variable's possible values. Trivially, you could just say every variable is in the interval negative infinity to positive infinity, but we want to create reasonably tight bounds. The abstract value of a variable, i.e. its interval, is an element of the interval lattice. The interval lattice is lift of LH, where L and H are numbers, and L is less than or equal to H. That's this lattice. Notice this lattice has infinite height, and if we create a state lattice mapping variables to intervals, that too will have infinite height. Our fixed point algorithm might not ever converge. We'll discuss how to cope with this in the next section. But first, let's define an eval function to abstractly evaluate expressions. This will be a function that takes in a state, which is a mapping of variables to intervals, and an expression, and determine the interval that that expression must reside in. So if we see a variable, we'll look that variable up in our state. If we see some number I, we'll know I is within the range I to I. If we see input, we'll have no clue what that expression's range is. If we see a binary expression, we'll abstractly evaluate each side, then abstractly combine the two intervals. To abstractly combine intervals, we'll consider the set of every possible value of each side of the expression and find its minimum and maximum. For example, if we see a binary expression where one side is between 1 and 10 and the other side is between negative 5 and 7, and we're adding them together, we'll consider every possible sum of x and y where x is between 1 and 10 and y is between negative 5 and 7. Obviously, this is minimized when you pick x to be 1 and y to be negative 5, and maximized when x is 10 and y is 7. Our join rule will find the least upper bound of all of our predecessor constraints, and our constraint for an assignment node v with the syntax x equals e will be to take the least upper bound of all predecessor nodes, but then set x to be the abstract evaluation of e. So we have a workable analysis if we could only be guaranteed that our fixed point algorithm actually terminated. Let's take a crack at that using a technique called widening. Essentially, our problem with our fixed point algorithm so far is that we keep on applying f to bottom. Every time we apply f, we move up the lattice, but if that lattice has infinite height, we can move up forever. Instead of simply repeatedly applying f, with widening, every time we apply f, we'll also apply a function omega. Omega is a coarsener. It'll take in a point in the lattice and jump up to a higher point in the lattice. Omega of f is guaranteed to converge. This is because we will choose omega that is monotone, extensive, and where omega of the lattice has finite height. Omega is also called a widening function. In the interval problem, omega can be defined as follows. We have a finite set B of integers. Omega of an interval will be the following. This will basically just find the tightest interval that contains the range L to H, where both bounds are numbers in our set B. Our widening function omega will make us lose some information in the process of finding a fixed point. However, applying f to our result will help us regain information. We call the reapplication of f narrowing. So in this example program, after the while loop, our analysis will diverge. We won't be able to find a fixed point because the y range is ever increasing. Say instead we widen using the set negative infinity, 0, 1, 7, and infinity. With widening, we get convergence after just 4 steps. Instead of increasing our range one at a time, we make a jump from 7 to infinity. But using narrowing, we can get x down to a reasonable range again. We only need one step of narrowing, because our constraint for x at the exit node will join together the intervals from x in the first line of code and from inside the loop. In both cases, x will be in the range 8 to 8, so we will get overall that x's interval is 8 to 8. Narrowing isn't guaranteed to converge, so you need to use heuristics to know how many iterations of narrowing to apply. There's a way of coarsening information that retains more details of the analysis. We'll call this more precise coarsener del. It's an operator that'll take in two elements of our lattice and return another element. Del will obey two properties. First, when given as input x and y, its output will be higher up in the lattice than both x and y. Second, if we have an increasing and potentially infinitely long sequence of elements of our lattice, call them z's, folding del over the sequence, starting with the first element of the sequence, will converge. Therefore, we know we can approximate fixed points of a function f by computing this sequence. We start at the bottom, and each successive element is the previous element, del f, of that element. Eventually, you'll have that x sub I equals x sub I plus 1. So our algorithm for computing fixed points as a whole will be the following. The overall idea of taking in two arguments as input in our widening function is that we won't widen every interval that is inputted, only those that are unstable, i.e. it's changing between the left and right hand sides of the operator. For example, if we define del prime as a widening operator on single intervals as the following, we will only coarsen the interval if the endpoints are unstable compared to the previous iteration. We can then use this del prime to define del.